Finally, let's talk about gradient gel. So I told you you can use a discontinuous gel that is made up with two separate gels. One is stacking gel on the top, the other one is a resolving gel at the bottom, right? Instead of using that discontinuous gel, you can use a single gel, which is called a gradient gel. So gradient gel is actually a mixture of two different percentage of agarose solutions, A and B. Maybe A has a higher percentage than B, and they are being mixed together when you make your gel. So when you pour in those two solutions together, by mixing them together, you can create a gel that has a gradient of polyacrylamide percentage. What I mean is, the bottom of it you will have a higher percentage, but when you move up through the gel, you will have a less and less percentage of your agarose because two solutions are being mixed together when you pour the solution. So that's called a gradient gel. So in this case, 4 to 12% gel you can make, meaning all the way to the bottom is about 12%, but all the way to the top is about 4%, and in between there's a gradient of acrylamide solution that's being poured in. So your gel will have a gradient of those two percentage. So that will give you the benefit of having two separate discontinuous gel in just one single continuous gel. That's the benefit of having a gradient gel. Okay, so you can have a good separation of protein molecules throughout the gel, because on the top of the gel you have a good separation of large molecules. In the bottom of the gel you'll have a good separation of small molecules, because there's a high percentage of acrylamide, there's a low percentage of acrylamide. So that's the benefit. Okay, so a lot of gradient gels are used these days instead of a discontinuous gel. Okay. And then how do you make those non-denaturing gel for electrophoresis? For example, that isoelectric focusing we talked about. So yeah, if you make a gel without the presence of STS or urea is another strong denaturant, that will become a non-denaturing native gel where proteins will be separated based on their charge, right? So the net charge of the protein depends on the pH. Of course, we talked about it when you talk about ion exchange chromatography separation, right? So surrounding pH determines how your protein will be charged. So if your protein is added to the pH area, it will actually try to migrate towards the pH where it's going to become net neutral. That's the isoelectric point. That's the pH value where your protein will become neutral. Right? So your protein will migrate towards isoelectric point where they will become neutral. That's how you separate out your proteins. So separation is governed by the pH, and the buffers used to have range of 3.7 to 10.6. You are creating a gradient of pH, okay, and you're going to add your protein, and protein will move towards the isoelectric point where they will become neutral. That's how the separation is working. Okay. So just like this, so if you have, the proteins added, so they will try to move towards the isoelectric point if you have a gradient of pH there, negative, positive, okay? So that's the charge-based separation. That's how that will take place. So different PI values, protein will move towards their PI value, okay? So the column gel can be poured, and then you can create a gradient of pHs, and protein samples will move this way. Or you can either do it on the slab gel as well, if we can create that pH gradient. So top is the sodium hydroxide basic, bottom is acid. So acid basic, there's a gradient of pH value, and your protein will migrate towards their PI value. That's how it works. Okay, I think that's the end of the lecture 5. All right, thank you.